So let's begin. So we are still carrying on our investigation of position time graphs. And today we're going to be looking at instantaneous velocity. Now I've neglected to talk about time interval and time instant. So I'll take a moment and talk about that for a second. What's the difference between a time interval and a time instant? Exactly 2 seconds. Like you said, an instant is exactly 2 seconds.
Like groups of numbers.
Groups of numbers, says Riley. Interval. Do you need Carly and Sarah? I need to listen, right? I've started. Don't get behind before we've gotten started. An interval is like over a period of time, right? You need like an initial and a final, and you need 2 readings, and then find the time interval you would subtract. Whereas an instant is simply a single reading of the clock, right? So an interval is like 2 readings. Colin, you put that away and listen to me. Okay? Everything I say today is designed to take you up to that big point at the end. You gotta pay attention right to start. So a time interval is 2 readings of the clock that you then subtract. You find out how long that time interval is. And an instant is just a single reading of the clock. And that comes into play here. So we're going to be calculating instantaneous velocity from a DT graph. Now we've talked already about average velocity over an interval, right? Distance over time. When I say instantaneous velocity, what does that mean? What does that mean to you? Annika, what does instantaneous velocity mean to you? At one, like how fast you're going, like right now, right? You look at your speedometer, how fast you're going right now. Whereas your average velocity is your average over that time. Okay? So, as you can see right here, so far we've determined displacement from a DT graph. How do we do that? Reading 2 points off the graph and subtract. And we've also determined average velocity from a DT graph. We've divided the displacement by the time interval. And here's our working one that we're going to be working with. Do you guys have this in front of you? Excellent. Okay. So, I think there on the side, we're just going to review. Okay, we're just going to find displacement and average velocity for those intervals. Now, is this something that I should let you try on your own while I go to make sense, or should I do a couple? Do a couple to remind you? Okay. So we're going to find displacement. I'll do the first 3, and then you guys can do the next ones. Find the displacement and average velocity for intervals A, B, C, D, E, and F, and those are the time intervals for them. Okay, so from 0 to 2 seconds. So interval A is this one right here. So what is the displacement? You look at the graph. The initial position is 0, and the final position is 6. And so our displacement is going to be 6 minus 0, which is 6. Okay, goes up 6. And our time is from 0 to 2 seconds. I'm just going to do this. And so my speed, my average velocity is 3 meters per second. And in fact, all I did there was find the what of the line? The slope of the line. All I did there was find the slope of the line. The displacement is the number on top. If we look at B, everyone's good with A? Yeah? If we look at B, we look at our initial and final positions. Well, the initial, it's at 6. The final's at 6. What's the displacement? 0. No big surprise. It's flat. How much time did that take? From 2 to 6 seconds. 6 minus 2, 0 over 4. 0 meters per second. C from 6 to 10. Now C is a fair bit longer, isn't it? Right? So let's have a closer look here. The initial position is the same as the final for the last one. So it ended at 6, or sorry, it started at 6, so I'm going to subtract 6. And the final is way down here at minus 10. So it's minus 10 minus 6, which is a displacement of minus 16. And if you want to count that, you can. But keep in mind, there might be some decimal values eventually. And how long did that take from 6 to 10 seconds? Well, that's 10 minus 6, that's 4. So the average velocity is minus 4 meters per second. Okay, you guys try D, E, and F. From 10 to 12, what do you guys get for an average velocity? It's flat, right? Do you even need to do any work? You shouldn't. 0 meters per second. E from 12 to 13 is this one right here. What do you guys get? 6? I'll take your word for it. Everyone agrees? Okay, but what do you do for F? Average velocity. I don't care what's actually happening. We know what this means. What's happening here? It's actually, what's the object doing? Savannah, I need you to listen. It's doing what? Slowing down. But I don't care because I'm interested in the average velocity. So all you do is find the average slope. That's literally all you do. Okay? So the final here is 0. The initial was minus 4. 0 minus minus 4 all over 18 minus 13. 4 over 5, 0.8 meters per second. Good for you if you got that on your own. Okay? Awesome. In the graph, the slope of the line and time interval A would be yield the average velocity, blah, blah, blah. Oh, yeah. This is true for straight lines and curved lines like interval F. I covered all. We're all good? Oh, do you? All of those paragraphs?
No, just part of it.
Oh, okay. I'll wait. Okay. So, instantaneous velocity is the slope of a line at a single point. Instantaneous velocity is the slope of a line at a single point, a time instant. Daniela, phone away, please. Okay? Should be on the next page. Instantaneous velocity. You need to fill in the slope of a line, whoopsie, the slope of a line at a single point, or a time instant. It's the slope at a single point. Now, it's on the back side, right? It says instantaneous velocity right at the top. Yep. That was exactly my question, Colin. I was just about to say, don't you need 2 points to find slope? And Colin beat me to it. Well, what do we do? Okay? Well, before we do that, let's just talk about straight line segments, right? It's easy for straight line segments. If I want to know the slope at A, like right there, or right there, or right there, or any point on any of these straight line segments, well, the slope is always the same. It's just the slope of the line, right? The slope at A is the same as the slope of A, right? The slope at 5 seconds is the same as the average slope for that entire line. And the slope here at 7 seconds is the same as, so you just find the slope. Okay? But what do we do? So V inst is the slope of the line for a straight line segment. And since the slope remains constant, that's why that's true. But the question is, what do we do when it's curved? What do you think you do? Any ideas? Now it looks to me, I'm just looking here, it looks to me like you have to do this, right? You have to fill that in there over on the right? Okay? So it's easy for straight line segments A, B, C, D, and E. The instantaneous velocity is simply the slope of the line, right? Since the slope remains constant. If you want to jot that in, you can. I got a little ahead of myself there. Yep, I'm still talking about this one though. Okay? I'm not talking about that bottom one. It's going to be on the next screen. Don't worry. Okay? So, how do I do it for a single point? The slope of a line at a single point, at time instant. Okay, instantaneous velocity, same graph, all I'm doing is here. For curved line segment F, you find the slope of the tangent line. And what do I mean by the slope of the tangent line? Okay? No, not the little button on your calculator. That is opposite over adjacent, okay? I've never seen this emoticon thingy here, but I'm guessing it means, huh? Right? How do we find instantaneous velocity? So, here's how it goes. Put your pens down, don't copy, just watch, I'll give you time. Here's where you actually learn how to do it. Okay, so instantaneous velocity using tangents. So a tangent line is a line that only touches the curve at one point and estimates or approximates the curve at that single point. So it's an estimate of the curve at that single point. This green line here is known as the tangent line. It's an estimate of the curve at that single point. Basically what you're doing is you're taking the little instant of line, like if you zoom way in, the curve, you know, if you zoom so far in, the curve becomes straight, and then you take that little teeny tiny straight line and do what? Expand it, straighten it out. Not straighten it out, but like extend it both directions. And that is your tangent line. And then what do? Then you find the slope. You pick 2 points on your tangent line, any 2 points. People like to pick endpoints. You don't have to. That's just a habit you picked up from math teachers. Does not have to be the endpoints. Any 2 points. It could even be 2 points on this side. It could be those two. That's fine too. And then find the slope. So just to clarify, when it's a straight line, you simply find the slope of the line. But when it's a curved line, you have to actually draw the line first. You got to draw the tangent line and then find the slope. Okay, what do you guys need to write down? So you've got your little graph there. Underneath it, it says tangent line only touches the curve. So you need to go ahead and write that. Underneath, all right, the tangent line only touches the curve at one point and estimates the curve at that single point. Okay? Both of those have to be true. It has to just touch it, just kind of come up and just kiss it. And it has to approximate or estimate the slope of the line at that single point. Now, is everyone going to have exactly the same tangent line? No. Okay? So how do we deal with that? Well, I insist on you showing your work. I look at your tangent line, and if it's close enough, and I see you've got 2 points, and you've done your slope calculations, and your slope calculation is kind of close to mine, you got it. If I have 3.5 and you got 3.55 or 3.6, no problem. If I have 3.5 and you have 47, not so much. Okay? It's got to be reasonably close, and you got to show your work. Okay, let's see what's under here. Okay? Pick any 2 points on the tangent line to find slope. You have that written down already. And V inst is the slope of the tangent line. And again, rise over run. There was a few people that were still confused about slope on the last test. y2 minus y1 all over x2 minus x1. You got to be able to do slope. And I think you have at the bottom there, when the dt graph is curved like this is known as variable motion. Why is it called variable motion? Because the velocity varies. The velocity varies. It increases or decreases. Curved up or curved down doesn't matter. Okay. Ready to practice one? I'll pause for one more second. Practice number 1. Now I realize that I haven't given you the best graph to work with because I don't have grid lines on there, right? But that's okay. It's all about estimating. All about estimating. So what I want you to do is draw a tangent line at that single point. Right? Draw a tangent line at that single point and find the slope to your best ability. Loading. Does it make it hard because there's no grid? A little bit. Even harder for me because I can't really put a ruler up there easily. Okay, so I'm going to put my ruler up here and I'm going to find. Now, is it better to have an X point or a Y point that sort of matches a grid? Doesn't, I mean, in this case, it doesn't matter, right? So there's my, you guys can't see the ruler, but I've got my ruler up here at 6, and I'm going to put this point like right there. Right, I'm just going to wing it here. So that's this point is at 6 comma, I'm going to say 22.5. And I'm going to pick another point. And just because I'm a little weird, I'm going to pick this point right here, both on this side of the dot. Is that okay? Yes, the slope of the line doesn't change. It doesn't matter what points you pick. Can be endpoints, any 2 points on the line. Any 2 points. So this point is at 4 comma, we'll say, I'm going to say 18. Okay? Will you have different points? Likely. And so what's my slope now? 22.5 minus 18 all over 6 minus 4. In this case here, that's going to be 4.5 over 2, which is 2.25 meters per second. Approximately. Do you guys know what the symbol for approximately is? Some of you do, yeah. Yeah, it's kind of like a wavy equal sign. Okay? A wavy equal sign means approximately. So if you see that, I don't think any of my answer sheets have that, but maybe some handwritten ones I might have done it that way, right? So if you've got a number anywhere between about 1.8 and 3, you're good. As long as you've done what? Show me which points you picked and done your slope calculation right. Give me the nod of understanding. I need to make a GIF out of that. The nod of understanding. I think it's pronounced GIF. Practice number 2, practice number 3's got a few of them.
Oh my gosh.
You try. Okay, let's look at this one here. This is practice number 2. If you want to just keep going, you go right ahead. You'll see the answer in a bit here. So I'm going to draw get my actual ruler out. I know you guys can't see this. Good one. That's the way my day's going. Now, does it matter? I'm purposely going to do this. Does it matter, you guys, that I cut the line down here? Does that matter? And the answer is no. Okay. We're only concerned with sort of like this portion, right? This part of the graph doesn't even exist in our mind. I only care. I want to find the slope of this, and if I have to go that far to find a good data point, then I'm going to do so. Bling any blinders. Going? Awesome. Okay, so now I'm going to pick 2 data points. I'm going to go right here just for fun because I know that's 10. 10 and we'll say 22. 10 and 22, and I'm going to pick 2 here. And 11. So I'm going to say 2 comma 11. So slope is 22 minus 11, 10 minus 2, 11 over 8. And someone help me out with, oh, here's one. They're 1.375, or we'll say approximately 1.4 meters per second. Did you get something like that? Around 1.4?
I got 2.
Yeah. Did you draw a line? Did you give me 2 points? Did you do the slope calculations right? That's all that matters. Okay? I'm pretty flexible on the number, as long as I can see what work you did. Now, Logan asked here, do we have to do different lines? Absolutely. You got to draw a tangent line here, and a tangent line there, and a tangent line there, and a tangent line. Now, this one's going to be kind of hard because it's almost straight at that point, isn't it? Right? Okay, so you can try those. If you want to continue on into the practice ones, you can. I was just down scanning the solutions that I made last night, and I'll get them. I'll get a sheet made up with answers. I probably won't get those to you till tomorrow, but I will get those for you because I want to put the link on there. Okay, I might get it by the end of the period here. So you guys keep going, keep trying. If you want to work on green sheet stuff, you can as well. You got the next 20 minutes.